Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my privilege today to introduce Professor Alex Weibel. Professor Weibel has positions at both Carnegie Mellon University and the University of Karlsruhe. So he always has an excuse when someone is looking for him one. He says, I'm in the other one. Traveling, racking up the frequent flyer miles. I've known him for about 15 years from my days at CMU. And he also is the director of the newly formed Interact Center, and I think he'll give a few words about this. Professor Weibel has been doing lots of work on neural networks, speech recognition, translation, both from text and speech, user interfaces, perceptual user interfaces, and a ton more stuff. And he'll be telling us today about just a snapshot of a couple of the projects that he's been involved, both from the European Union funding as well as U.S. funding, and a few of the other activities that his center is engaged in. He's also Associate Director of the Language Institute at CMU, as well as many other positions, but I can't keep track of all of them. So without further ado, Professor Weibel.
Thanks very much. This is working? Okay. Thanks very much for the kind introduction. It's always fun to be here, of course. Last time I visited probably was at least 2-3 years ago, maybe. So it was high time I figured to come visit you again. This stuff about always having excuses to go to nice places, usually that I go to the other place when there's a holiday in one. So, usually plenty of work to do in both places. But what we're doing is there's really one big vision in all of what we do. It is somehow facilitating or making human communication easier, more friendlier, and more fun. And so what I will be talking about today is, I entitled it as Modeling and Facilitating Human Communication. Before I do, let me just simply spend one slide on explaining to you what Interact is. We have worked for 15 years between these two places, Carnegie Mellon and University of Karlsruhe, and it's been recently that so for those 15 years it was mostly tolerated that I was everybody claimed that I was always gone, and that I spent a lot of time on airplanes, which obviously was true. But in the meantime, it's been seen as a real strength of this cooperation that we've done, because students have over the years had a chance to really go do their projects in the other country and really do the same research that they would do normally in the lab, but work with an international team and get to know 2-3 continents and essentially learn how to work with people in different countries and so on. And they love it. So we've graduated numerous people who've done diploma thesis or master's thesis or PhDs and so on in sort of this cyber way, if you want to call it that way. And so it's been recently that the state of Baden-Württemberg and Carnegie Mellon both decided to actually kick in some money and to create a little formal infrastructure for this to not only facilitate this type of exchange for us, but also to broaden it a little bit to allow it for other areas of research as well. And so we launched this in the beginning of this year. The two presidents of the two universities came together and signed a formal agreement and so on. We now have some funding also for providing student stipends. And the notion, of course, is that we graduate students who are more well-rounded while at the same time also working at state-of-the-art research. And hopefully that's obviously interesting to big companies like your own. So there's, of course, it's a center. A center is an administrative entity and also a research entity. It's not a department. A department is an educational entity, so we're affiliated with various departments in Germany at the University of Karlsruhe with the Informatik department, the computer science department, which is ranked in German rankings as #1 in computer science. And obviously you know that Carnegie Mellon is generally at least sharing the rank #1 with the 2 other places. So we really have a good combination of people who view themselves equal. So it's not also an export of education, but really a cooperation between 2 leading institutions in the 2 continents. So at CMU, we're affiliated with the Language Technology Institute, Human-Computer Interaction Institute, and the Computer Science Department. The mission of the center, as I mentioned, is to facilitate that student exchange and training, but also in the spirit of eating our own dog food, building technologies that should facilitate human communication, particularly when you're distant, when there are different languages involved, when things in fact aren't sometimes easy to communicate. So as part of this research vision, I'd like to talk for the rest of the talk about 2 main stories which were or 2 main hot buttons that we're very active on right now. One is called CHILL, Computers in the Human Interaction Loop, and the other one is something we've been doing for many years, of course, is speech translation, but that's also taken a new and interesting twist, I think, and I will tell you later what we're up to there in this area. So let me begin with the first story, which it all relates to, I think, this picture where we're saying computer interaction with computers. When I was a student, there was no interaction. I remember my first summer job. I went out and looked at the instruction set of, at the time, LSI. I don't know if you remember this. Reveals my age, but it only had 1 instruction for input and output. You could put a character out to the screen and you could take a character in from some device. That was it. And that to me was just shocking, because what else should a computer do than somehow interact with human beings? So of course many years later we've now spent a lot of time with improving mostly human-computer interaction, but and in fact probably most memory and most processing power today is expended just basically for this interface. If every time a bigger version of Windows and PowerPoint and so forth comes out, usually what gets added is pictures and sounds and things like that, which is all something for the human experience that makes it big. So that's made it better, but things are not all good. We still generate a lot of requirements for human attention in this human-computer interaction, and so we still everybody has these jokes about computers basically making humans to their slaves, where we all have to sit at the machine and do what the machine wants us to do. So there's other communication. So one is having a machine operate on data sources like television, broadcast news, databases, and so forth. There's a ton of it now out on the net that involves human information. And then the 2 that I'm talking about, one is to have a computer that mediates human-to-human communication, so human-computer, human communication. And the 2 big areas where that's necessary is distant and language, where you really have a separation between these people and you want the machine to mediate. And then the other, where you really just have human-to-human communication, and the machine observes that interaction between the human beings and tries to provide implicit services. And that's the first CHILL story I want to tell you about. CHILL stands for Computer in the Human Interaction Loop. So the idea here is we don't look at how humans interact with computers, but we look at how humans interact with humans, and the machine hovers in the background trying to provide some useful assistance implicitly without you ever requesting it. So think of it like a smart secretary, a smart butler, a smart assistant that is your personal assistant to do this for you, with the hope of requiring as least possible human involvement, actually explicit involvement. So the vision there is to observe humans engaging and interacting with humans, predicting needs and proactively providing services, and then detecting, alerting, triggering, or information services based on that. There's 2 outcomes that we hope from this. One is the scientific outcome that really should push us further into a fuller understanding of what human communication is about and how we process it and how we, in fact, handle it, how we understand it across all modalities. And then robustness and perceptual user interfaces. On the societal outcome, the big hope that we have is that it reduces the need for human attention and reduces the preoccupation with techno-clutter. We all have, even as computer scientists, we hate having to do lots of silly things that have nothing to do with our day-to-day activities, but that are essentially preoccupations with what the machine forces us to do. Now, the idea is obviously to use a better understanding of the human context to make that better. So we proposed that to the European Union, this project or this idea. The European Union has recently created or started this framework program 6. It's a new program under which they are now funding these so-called integrated projects. And integrated projects are, in difference to what they did before, fewer but bigger projects, while before there was more and smaller ones. And so they were in the multimodal, multilingual area. They said they would fund 3. And so we wrote 2 proposals, one for speech translation, one for multimodal. And we got actually both of them funded, which made us quite happy. And this CHILL project was one of them. It's probably the biggest of these IPs in this area that was funded in this first round under this 6th framework program. There's 15 partners involved from 9 countries. The total budget is 25 million euro for 3 years. These 9 countries represented there from Europe and the US. In the US it's IBM, Carnegie Mellon and Stanford involved in this work. I'm the research coordinator of this project. There's a financial coordinator from the Fraunhofer Gesellschaft managing the administrative side of things. And the first term is for 3 years with the hope or possibility of continuation later. This is a list of all the partners. Let me just move on beyond that. And so if you now say, okay, if you want to have the smart, so what's the technical thing underneath? If you wanted to have a smart assistant or a smart device that could really help you, understanding the human context is critical to do this more proactively and more intelligently. But consider for a moment what that would take. If I asked you after a meeting, why did Joe get angry at Bob about the budget? You know, what information do you need to know? You need to know that Joe was present. You need to know that Bob was present. You need to know that Joe was addressing Bob when he said something. You need to know that the emotion was angry. You need to know that what they were talking about is budget. You need to have some sort of inference about the flow of the dialogue. And already I listed here half a dozen technologies that each one of them is just enormously difficult. How do you detect people in meeting situations when they're really not producing nice mugshots for you, but running around and producing occlusion, etc. So there's verbal and visual information. Speech is obviously recognizing the words. We've done a lot of work there. But speech has more information, knowing the speakers, the emotion, the genre, language processing, summaries, topic, handwriting, visual information, blah, blah, blah. What is it all about? Well, what we really want to know is something functional about what people really do in this space. So these are all pieces of information, perceptual elements of identifying who is there, what they are doing, where they are, why they are doing it, and how they are doing it. So we call it the who, what, where, why, and how of this human communication that we're after, and speech and visual information and maybe other senses are in fact an element in that process. So we set out to now analyze how can we track who, where, what, why, and how, and broke that down into traditional research fields that people have used to answer part of these questions. Notice that some of the traditional things, are being done, but then there are certain other things like audiovisual person tracking really requires finding people, or person identification is not only visual face identification, it's not only speaker identification, it could be a whole bunch of things that you could do to detect people. So this is, of course, a grand challenge, and so with this integrated project we had a chance to take a whack at that. So we broke this down into various layers. One is a service layer which thinks about the services that you could be doing if you had all this information. If you knew who was in the room, what they were doing, why they're doing, and how, and so forth, what kinds of new things could you now be doing at the level of a service or a product or a human computing service. Study the success of such services and their ability to improve productivity. Not everything that we think as computer scientists is useful winds up in the end being useful. We don't want to create another big nuisance in the end rather than something useful. Then there's again the technology's functionalities, like I described, detecting these pieces of information. Again, these underlying technologies have been studied before, but we need to really go to another level of robustness and another level of integration to be able to properly understand answer these questions. There's some infrastructure, some plumbing, architectures, software environment, and so on, which is also part of the project. And the scenarios that we have chosen is situations of meetings and lectures with the emphasis on something that is clearly natural. So we're recording normal seminars that we have in our lab. You'll see images of Mike Seltzer giving a talk at our lab a little bit later. So just whatever happens in our space gets recorded, and that becomes essentially the environment. So we're not trying to influence the way this comes out. Here's some of this. So we could, of course, not just ramble on and say something, okay, wonderful services. We had to be concrete at least about a couple that we really wanted to implement, while the project also allows a great deal of flexibility for people to come up with additional ones. Let me just tell you about two of them that our lab in Karlsruhe, again, I mentioned there are 15 labs involved, and services are being actually developed by 4 of them, or 5. There's UPC in Barcelona, IRST in Italy, AIT in Athens, Greece, and us at Karlsruhe, and I think IBM, Yorktown Heights, is also involved in one of these. We are involved in 2 of these, connector and memory jog. The specific idea here with the connector is imagining a cell phone or a communicator which is smart enough to know what your activity is so that it can connect people when it is appropriate to connect them. So if you're in a lecture, you don't want your cell phone to ring. If I'm giving a lecture, particularly I don't want my cell phone to ring. I don't even want it to vibrate, except if it is my wife calling because the house is burning down, right? If my wife was just calling to say hi, maybe it should delicately tell her message. I'm just about giving a lecture and she would understand. But if something emergency happens, so what does that mean? We need to know something about the context, what we're actually doing, the activity. We need to know something about the environment that we're in. We could be sitting here in this lecture room just playing cards. So environment is important, but the activity is important, and then also the social relationships between people. Who is actually interacting with who? Certain people should never call me, and other people should get, immediately patched through. So that's something that the connector would do. Connect people in any media at the appropriate way at the appropriate time. Memory jog is another idea where we're looking at a device or an assistant which gives you information about things you're likely to forget. People's names, forget where you left the remote control. People spend more time looking for remote control than it would take to actually go to the TV set and switch the channels. Elderly people, where did they leave the medicine? Did they take the medicine? And so on. So reminding people of giving them information that they may have forgotten at the right moment is one such idea. Again, notice that all these services have in common that they should do this implicitly. They should provide this information without you actually requiring to do a great deal of interaction. In fact, saving you time that way. Connector, for example, would save you time by not having you play phone tag with people. So one other thing we built over the time is a meeting browser that lets you review meetings. But let me say more about evaluation. Evaluation is a key in this project. We do a great deal on benchmarks. Again, with something like this, you have technologies that can be benchmarked. We call that the MOPS, the measures of performance, and the MOS, the measures of effectiveness, is then more the question, does this thing work? Is it fun? Is it a nuisance? Do you like this? And so on. So with the functionalities and the technologies, we formed early on a working group. They are up and running. They have databases and benchmarks. If these databases and benchmarks already exist in the community, for example, by way of DARPA programs, the team just participates in those DARPA programs, and for those that there is no benchmark, we create and set up new ones. We did a first dry run already 6 months into the project. That happened in June. First results were reported, and there's another one coming up in 2004 for a variety of these technologies. With services, initially we're just simply doing this in a rapid prototyping way, where we build, everybody who's doing services builds demos, and we go around and compare and contrast and learn from each other whether these things look cool, whether they're working well, etc. And in the meantime, Clifford Nass at Stanford is working with us to come up with better usability measures, and then also better studies of the effectiveness and usefulness from a human point of view of these services as they get developed. As a first-year technology task, this is a list. Let me skip down right away to, this is the room of the data. I'm sorry. Okay. So in the first year, we sat down we had a working group that really looked at the service that we want to do and implement and say, what are the most critical technologies we should be implementing? And then they came up with this laundry list of items. And then each one of the different, again, keep in mind that in this big project with the 15 labs, we have people who are very well known and long-term in the speech community. We have people who are long-term in the vision community. So we really have people in these groups who represent state-of-the-art technologies in each one of these areas. And they formed then mini-groups to define what are the benchmarks, what kind of benchmarking should we have in order to come up with technologies that will work for these services in mind. And then this is the laundry list that they came up with, and the ones that are not italicized are the ones that we already ran a first evaluation in June, and that will be continued. So the first data that we used in June is in fact seminar data we recorded in our lab. So Karlsruhe in fact distributed that to all the partners. And there's now additional data being collected by every one of these groups that are doing services. There's some data collected in Spain, some in Italy, some in France now at LIMSI. LIMSI is part of this effort in France. And each one of these labs has a room with cameras, microphones, microphone arrays, fish-eyed cameras, so a whole bunch of sensors to provide a database based on which we can then study this in detail. I think most of this I already said. One point, though, is the question of language comes up always in a European project, and usually the question gets answered by having the whole project do everything in 5 languages, thereby diluting the funds a great deal. We came up with a new clever argument. We said we do European English, which essentially means accented English, the kind of English that is spoken in the European community when people come together for meetings. And that actually has gotten an accepted argument recently because we want to focus on the actual science and the research and not just do a lot of make work by porting it to other languages. Again, the scenarios are meetings and lectures, and well, we sort of did the first one here. So here you see an example. This is Mike Seltzer, yours truly, in Karlsruhe, giving a lecture on his work with a microphone array. And you see him giving the lecture here from the point of view of 4 different cameras in the room. That's part of this database. There's also, of course, audio tracks from multiple cameras that come with this data. And that type of data from several speakers was then distributed to all the sites for doing their research. What you see here, these blue set of flies is a particle filter that was one of the experiments used by some students in our lab to help identify the person tracking, and also find the face or the head in the image. Notice that all of this is a little tricky because the head or the face or the hands are only a small part of the image, so there's of course resolution problems. There is also a great deal of variety, so a lot of past work has concentrated on rather artificial recordings of people, mugshots and clean image image sequences and so on, which is obviously not the case here. Speech recognition, so there's a lot more variability and sometimes also occlusion when people are standing in front of each other. Yeah.
So was that blue stuff all done basically just using the cameras, or was it using audio or any other clues?
That was just the cameras, yeah.
Independently or together?
Independently.
And at some point, one of the persons in the audience moved, and a box went around his head with no blue stuff.
Right, good question. I can't answer the question.
Okay.
I always have blue stuff.
Like
That's not the track? Yeah, exactly.
Yeah. I mean, it reminds me a little bit of many years ago, there was a microphone array in the Murray Hill Auditorium.
Right.
And they had a bug in it that if anybody kibitzed to anybody, it went over the house speakers.
Right. So actually, right, I remember this work where the idea was in fact even tracking having the cameras track whatever the sound source localization of the microphone array would do. I
saw one like that, and it would aim the cameras at the wall because the reverberation was the strongest sound in the room.
That's right. Well, you have a door slamming and it would veer off in this direction. So we do it the other way around. We orient the microphone array in the direction of the face that you want to track, that comes from the camera. But again, even tracking faces isn't as trivial when you have to deal with occlusion and people moving in front of each other. And I'll show you some pictures in a second. Or like here in this case, where somebody walks in and it's close enough, and for a while this particle filter actually gets confused. So speech, I don't have to explain, but I'll have later some examples. If you build a broadcast news recognizer, in most of our experiments we're below 10% for English, Chinese, and some other languages. But if you take the same, and that's sort of what recognizers go for these days, but if you now take them to more, and to a situation where you put a lapel microphone on people in a meeting, in our research group, a research meeting, and let them just talk with each other, then error rates go up to 50%. So things are still pretty grim in that area.
The first two meetings, close talking meeting versus desktop meeting, or the first two? But
they were all lapel microphones, so they neither close talking nor desktop.
What's the difference between the conditions for those two?
This was an improvement we had done at the time. Two different trials with two different adaptation algorithms. I think here what happened is we actually trained the language model on meeting data, which we didn't do here. So the big problem here is, of course, in the case of speech, is that you have mismatched conditions. You have remote microphones, etc. You have different speaking styles. You have different language models and vocabularies. If you have a meeting or a lecture, people don't come into lecture rooms and tell you the broadcast news of the day, but they tend to speak about very specific topics, with very specific words and vocabularies. Another interesting thing that I like to always point out is that if we really want to build these implicit services, one important element is that ideally the recording is always on, and the transducer is not necessarily optimally placed. And in the case of speech, you don't wear a close speaking microphone. And not having a close speaking microphone and not having an on-off switch poses all kinds of additional problems all of a sudden, because now this whole remote microphone problem is a huge one in speech, and then to deal with crosstalk and noise, but then also not knowing when the speech actually begins and when it ends. It could be the vacuum cleaner of the janitor at night that you're picking up instead of some lecture. So the microphone positioning, again, I don't want to bore you with a lot of details, just want to show you some examples.
11 European countries.
So as humans, we don't really hear a big difference between these sounds, but it's a remote microphone, and if you don't know the characteristics, that's the problem. We can, of course, always collect a lot of data with a particular microphone distance and get a wonderful recognizer, but if you allow people to randomly walk around a room, it's actually an enormous challenge and a really big problem to do this well. So this is one part of the work that's going on. Another part that is big, again, for those of you who are speech people, you know that, but it came as a surprise when these kinds of experiments were done for the first time, is how much degradation you get just simply from conversational speech.
I think you were saying that they try to influence, but it's... I think you were saying that they try to influence, but it's...
So we redid essentially following an experiment that was done at SRI a while back, where they did this. We replicated a similar experiment where we took these meeting recordings and we asked the same speaker with the same microphone to read what she was saying in the meeting exactly the same way.
I think you were saying that they tried to influence, but it's...
So it's the same sentence, the same speaker, the same microphone and so on. And the error rate is 1/2 when people read it from when they actually speak conversationally. So again, a big gap just purely based on conversational speech. Crosstalk.
The recording is for me.
We found that in telephone conversations about 10% overlap when people barge into each other. In meetings it's actually 30%. So in meetings people like to talk on top of each other. And it's actually an enormous problem. Whenever that happens, most basically current technology simply fails. Sometimes people do strange things in the middle of a...
Yeah, Agassiz number one.
So this person laughs in the middle of the sentence, and that laughter, of course, generates confusion, because it's an additional spurious sounds on top of the speech. We also, in order to get people to record this speech, we gave them pizzas to attract them to come to our lab, and we found that was a big problem, because now we get munching sounds on top of the speech. So many of our experiments, we use the JANA speech recognition toolkit. You know about it. I think one of the things that we specialize here with this recognizer is that we've done it on many, many different languages. We've worked on 15, 17, 18 languages with this recognizer. And, of course, to the extent possible with our funding, we participate in this DARPA evaluation. Last one was the meeting evaluation in 2004, where we got some quite reasonable results. Most of what we do there is adaptation, I think. Adaptation. Try to adapt to the sound situation, the language model, dictionaries, noise, and pronunciation, acoustic models. Let me skip over this because I may otherwise run out of time. Just give you one interesting now variation. So what we've wanted to do is, from broadcast news and conversational speech, look at two particular instances, as I mentioned before, meetings and lectures. So lectures really hasn't been looked at very much from speech recognition community. So we set out, again, these seminars that we recorded are lectures of sorts, but we started also just simply recording lectures in classroom settings. Here's an interesting one. That is, in fact, a lecture I gave. It was an introductory lecture on speech recognition, where I explained to the student what the vocal tract does and what the vocal folds are doing and what the articulators are doing.
I can keep the pitch constant, ow, yow, and produce all kinds of vowels just by modifying the cavity, but not changing anything in the vocal folds. Okay, so we have these two components. You can also excite it in other ways. You don't necessarily have to vibrate into it. You can also hit it.
So you see, I'm actually playing with my articulators, creating noises that aren't words, and people wind up doing stuff like that in lectures or in talks and so on. And obviously where that happens, the recognizer really doesn't know what to do with the ROE when I'm playing with the thing. But other than that, actually, the outcome was surprisingly good. We didn't do anything special on this recognizer. We just ran it on my lecture speech, and we're actually surprised that by and large, it didn't do all that badly. Yeah.
The breath and the fillers, are those coming straight out of the recognizer, or they're post-processing the recognition output?
Straight out of the recognizer. We have noise models. I couldn't swear to it, but typically what we do, and in this particular example, but typically what we do is we have a noise model in the recognizer, and then it basically produces them just like you would words otherwise. So another thing that we started then looking at is there is this database called TED. It's distributed by ELRA. It's 1993. I think Limsey or somebody recorded all of Eurospeech 93, every lecture, and put it on a CD and distributed it. Nobody ever did anything. It was so gruesome of a database that nobody really worked with it. And so we dug this up and started working with it and producing some results. TED stands for Translingual English Database, but it's effectively also in the community known as the Terrible English Database because of what I will show you in a moment.
The second category is verbal elements. These are verbal attributes which may or not be present within the dialogue. They affect the structure of the dialogue, and their combination is unique for each dialogue structure model.
So what I'll give you is sound examples and then also show you what the error rate is of a system playing on those. So you get to guess a little bit how good the recognizer is likely to be when these different...
Give out the recognized words with their starting and ending time frame, besides their acoustic likelihood.
The involved objects betray verb. This is illustrated by this schemata where a meaning link is made using rules between the form of a neuteron.
For the written case, we had 9 subjects and we collected about 500 utterances. The average sentence length is about 8 words by query,
which I'm going to show you now. And strikingly enough, you don't see any shift from the 5th to the 6th generation.
Notice you also have very noises by paper rustling. You have, huh?
That's got to be the worst.
when you can't make any sense of what is coming in, okay? Now this applies at all of the levels. I've indicated something here. First, you assume that you are getting...
German somehow, we always find the German accent tends to be rather good. In fact, in our own lab, we use German speakers to give good demos, while our American speakers on the English systems usually get worse results. Japanese and French tend to be always, in our experience, tricky to handle.
The inspiration for the exact manipulation of the stimuli was derived from pilot experiments in which we use
both speech and its role for naturalness are reported. But it is also difficult to generate a fluctuation component.
But it is harder, so Japanese accent tends to be actually difficult.
Do you know what the OV rate was?
I'm sorry?
The OV rate.
I don't know.
Did you retrain the language models on in-domain data?
Well, I'll tell you a little bit in a second. The overall performance right now is about 30%, and we started with about 80% error rate. And part of the way in which you get down the error rate is in fact adapting the language model and the dictionary, and you do this iteratively by pulling in. So one technique we're using, which goes in the direction of this adaptation, is take the talk and take the slides. We also have access to the slides and the papers of this, and now take those as queries into web searches where you pull out even more documents which contain all these special words. You know, you have things like capture coefficients and filter bank and so on. That's not in broadcast news, so you have to go look for it. And by doing web searches with this material in hand, you actually get quite a bit of improvement here. So if you have lectures, then obviously you can do web searches, and that's in fact what we then, lecture searches, and also lecture summarization. In both of these areas we have some activity going on. Let me just skip over this, how we do it. It's basically statistically driven summarization where you are picking out salient parts in a talk that may be interesting for people to review. This is something we did last summer. We had lots of fun in Barcelona. I was telling Alex about this. The Barcelona city government has created this big forum of cultures which has these fancy themes, among other cultural diversity. And so we've been saying, cultural diversity, how do we maintain cultural diversity? And we say, well, language technology. We can let everyone speak their own language and still bridge the divide by technology. So we teamed up with some people from China that in turn have links with the municipal government. This is the mayor of Barcelona, who has been sponsoring and supporting our activity for many years. And we sort of had this big technology day in July where we showed this to the public. It was just before ACL. For those of you who've been at ACL, you may have seen these demos. We had them also displayed at that point. There you see this multimodal table. What this multimodal table did is we had a seminar before this event which recorded all of the lectures. It was about, I think, 10, 15 lectures. And each one of these lectures was, during that week, automatically transcribed in Italy and in Germany. And the results were sent back for then indexing and retrieval. And then at the end of that week, when we had this language technology, people could access the snippets or interesting parts of the talks through this table or through direct queries by voice. Or actually, if you notice here, the most challenging one that we find quite interesting is down here in the middle. You see a little button, if you look carefully. That's a microphone. So we had a microphone in the table. And the idea here as a sort of chill service is you let people just talk to each other about their experience at ACL and so forth. And whenever something is being said that relates to a lecture that is available, there's, I know something about it. And then on the wall, there's a waterfall of keywords and interesting topics where whenever you said something, multilingual speech recognition, it kind of says that on the wall, and you can then pick a part of a lecture that talks about that. So it's an idea of providing an environment in which you always are presented with relevant information that relates to your current interaction and your current discussion. Well, on to other things. Just wanted to point out that speech is not only recognizing words. So even if you don't know what people said, you can usually tell a lot of other things from voice. You can tell the language, you can tell the acoustic scene. Acoustic scene is a particularly interesting one. I try that on my students all the time, that I call from random places and ask them simply point blank, where am I calling from? And then they listen for a while and they can usually tell it's a Japanese airport or a German railway station or things like that. And it's just based on the sound scene. It's remarkable how well we do that. And so we are now beginning to look at that as well. Emotion, discourse analysis, speaker identification, topic ID, entity tracking, all of this can be done partially also without the words. This is an old story here already with emotional speech. We can
go to sleep now, go to sleep now, go to sleep now, go to sleep now.
So it's possible to recognize the emotions, but it's also possible to do something special to recognize emotional speech, which is also tricky. Both of them are real research topics, trying to extract the identity of the emotion, but then also recognize the speech despite the emotion, which is another challenge. So here's something about scene analysis. This is a day in the life of Rob Malkin, who is the PhD student at CMU who's working on
Testing.
So he recorded his whole day, and the system automatically slices it into interesting things that happen or salient things that happen.
So I'm very like playing.
Oh.
I said, it's me, and he said, oh.
I'm sorry. So damn slow to make sure.
So the point of this is you can actually segment a day into certain events, and we can all sort of know roughly what happened during this day. You know, he was in a computer room, then he was walking outside and the birds are chirping, then he was talking to his wife, and then he must have been sitting in a bar or something, I don't know, a cafe with music. So there's these things, these acoustic scenes, and we subconsciously always know what they are, and they give us a setting, a context. We understand things in that context. And again, for chill, that's of course very important. So we have an activity there to do this acoustic scene analysis, identify that environment in which people find themselves. There's also, of course, people tracking. You can track people based on simple features like motion and sometimes color. Here again is another, the other one that I already showed you, the particle filter. This is another piece of work where we're trying to track people based on multiple cameras when they're occluding each other. So as they're walking around, they cover each other once in a while. If you do that from one camera, obviously you lose track of the individual person. And so if you have 4 cameras, you can extract them from each other, but you have to coordinate the 4 cameras and know which dot belongs to what dot. And so that's an area that's actually being pursued, and that is now also part of this benchmarking activity. So we have a 2D and a 3D person tracking activity that is being benchmarked to see how well we can actually do this task, because it is critical. Here's another one where the idea or the task is more, now that you know where people are and where their faces are, can we track their faces and their hands in order to see what their hands and head are doing with respect to each other, in particular for pointing gestures or or activities that involve the hands. That is information that is important. One little application we built for a demo is something that connects with voice, for example, where you see here it's tracking the hands and the head of that person, and as he says something, the computer model then produces a trajectory, and that trajectory is something then that gives you the point of reference that the dialogue refers to, like turn that light on, or switch that off, or kill this, delete that. You don't want anything in the room deleting anything just because you said the word delete. So you want to make reference to what it is actually you're relating to. And that requires, again, vision, speech, and all of these things together. Here's another story that's quite interesting. When you have people's faces sitting around a room, we use a panorama camera that takes a 360-degree view of people. It extracts the faces from these people and then tries to identify the pose, the orientation of the head. And then given that information, you see here the people's heads are being extracted, and then as they turn their head, there is a system that finds the orientation of the head, and based on the orientation of the head we can then make inference what people are looking at, and then try to infer from that again what the focus of attention is. Notice that focus of attention is correlated with head orientation, but it's not uniquely determined. You have to combine head orientation with other pieces of information which we call interesting sources, targets of interest, targets of potential interest. So we usually take, if I'm looking in this direction, for example, chances are I'm looking at Alex Acero, not at the doorknob behind you, because we assume that human heads and faces are more interesting. And similarly, if there's a loud noise somewhere, or if somebody mentions somebody's name, all of these are correlates to where human interest and human focus goes, and it goes into a statistical model that combines all these pieces of information. People identification. We look at speaker ID and people ID both at the same time and merge them. Just wanted to point out here that it's tricky because you have different illumination problems. You have head pose. You need to recognize faces despite different head pose. And then occlusion. That to me has been also a big surprise. It's 30% of the time in meetings, people do funny things with their faces. They put their face in their mouth, and every time I talk about it and look in the room, and 30% of people do it, and then they quickly take their hand down as I'm talking about it. But it's happening. People do this, and that obviously complicates it. So we need to have people identification, face identification methods that are much more robust and much more opportunistic. That they take, in fact, the images when they present themselves as a useful recognition. So let me go to I have an hour and a half altogether, right? Including Q&A. So let me talk a little bit about human, machine, human, which is the speech translation story. Part of that speech translation story, of course, involves speech recognition, and I already told you about that, so I can skip that. Let me focus here mostly on what we're thinking about here in the machine translation area. Now, we've done for many years build these kinds of devices where you have tourist translation systems that people wear, or PDA systems. We've done the story there always that we point out is that conversational speech is hard. You have this random stuff, and translation systems will not work well on this. Text translation systems will not work well on such spontaneous speech, and often the message is in fact very simple. That people just didn't really, they mumbled a lot, but there is some very simple message they wanted to get across. So extracting key meaning or reducing that meaning to the key, that message to the key meaning that you want to translate is an important element of that. Oops, going in the wrong direction, sorry. You also know that we formed this consortium C-STAR, which has been operating now for 15 years. It involves many laboratories, and I would say there is 4 phases or 3 or 4 phases that we've been in. In this first phase, when we formed this consortium from 90 to 92, we built the very first speech translators, and people just, it was wow, this could be done at all. But they were kind of hokey because they followed a restricted language and a restricted language model, restricted vocabulary, and so on. So you basically needed to know what you could say in order to be translated. So we moved then on for another 7 years to build systems with spontaneous speech. So you could say anything you wanted to, but you had to stay in a certain limited domain. So you have to say, you can say it any way you like, but it's only about hotel reservation, or only about scheduling, or only about doctor-patient dialogues. Each one of these is, of course, important applications. So, lots of people would be happy if that existed, even within that domain. And so, in fact, a great deal of activity now and in the past has been focused on making this more portable, more robust, and apply it to real-world applications. Now, to me, so this is an example of one of those systems, as I mentioned. This is one of our PDAs that has been doing that, this is a doctor-patient PDA developed for DARPA between Arabic and English, so you could in fact have a doctor-patient dialogue between Arabic and English. We built these video conferencing systems with web-based travel support. Something cute I couldn't resist putting in here as a slide is this thing, where we also manipulated the video.
お支払いはどうされますか?
How will you pay?
Ich würde gerne ein Doppelzimmer für heute Nacht reservieren.
I would like to reserve a double room for tonight.
So the idea of this, of course, was a master student of one of the students to just do a artificial manipulation of the lips, map it onto the phonemes of the target language, and try to see whether you could create actually the video illusion of the original person speaking the other language. Now, where does this all go? I think the big limitation here, again, first it couldn't be done. Then we showed that you can do spontaneous speech. But one of the big limitations here always was always in limited domain tasks. And so we said, in order to do spontaneous speech, let's take advantage of the semantics of the task. If we know that it's about hotel reservation, then we can go into corrupted spontaneous speech and look for the nuggets of information in order to fill in a semantic representation or interlingua, and then with that go into the target language and do the synthesis of that sentence in a clean and usable way. But it's of course then limits it always in terms of that limited domain. So our hot button these days is to see, can we do domain unlimited spontaneous speech translation? And that's, I think, the new challenge for the next coming years. We have 2 new grants that give us a chance to actually explore that, and so this is going to be actually quite exciting. So let me flash through this really quick and show you what some of these things are. Most of you probably know about it, so I can do this quickly. You know that there are 3 approaches: direct transfer and interlingua approaches in general text translation. Interlingua approach has the advantage that it can allow in speech translation systems paraphrasing back into your own language. You can connect multiple languages with multiple languages. You know, it's one thing to talk about Chinese-English translation, but to get Catalan-Swahili or something like that is a language pair that you will find very difficult to get translation systems. So having something that goes through something in between, an interlingua, has a practical advantage. Then other advantages are, in fact, eliminating disfluencies, cleaning up the language, and generating a more culturally, contextually appropriate interpretation of that sentence. We also, in the world of text translation, we are part of this DARPA TIDES program, which is now funding very big effort text translation things. We're following a statistical machine translation approach. I would say that the statistical machine translation approach for us currently gives the best results, but it has obviously another constraint, which I will say in a moment, namely that it requires large, big parallel corpora in order to train it or build it. You know how this works. It's basically another source channel model, similar to, akin to speech or analogous to speech. There's an alignment then that is being done. This, by the way, is a slide from, we did this back into the 90s. Ye Wang did his PhD thesis with that, your colleague. And in fact, he looked precisely at some of those problems that happen when you take direct statistical machine translation and extend it to spontaneous speech. Because in spontaneous speech, you have these garbage phrases which you'd like to eliminate. And again, in the statistical project presents a problem. And Yi made some very nice early contributions to this problem. Again, the problems or the advantages are, or disadvantages. Interlingua has the advantages that you can port to new languages. You can get new language pairs sometimes for free because you can just plug them together. But the big problem is domain limitation and the effort to program the grammars and to define the interlingual representation in the first place. With the statistical machine translation approach, we can do broader domains. It's automatically trainable from parallel corpora. We don't have to write rules for it. But it's mostly for text, not for spoken language. There are no parallel corpora for conversational speech. And what does it mean to have a parallel corpora of spontaneous speech? It's even hard to imagine what that should look like. And it costs a lot of effort to create these corpora, particularly if you're looking at any language pair. It's okay to do Chinese-English. There's a ton of data there. But as I said, if you have Swahili-Catalan, it's much harder to find such databases. One activity at CMU is also to look at multi-engine things where these different approaches are combined into one joint translator, which tries to get the base of multiple words. But we wanted to now actually look at the problem of what happens, first of all, if you take these systems, and 2 problems that I'd like to spend the last few minutes on is what do we need to do to dramatically reduce the cost to go from some standard languages into new languages, which is a huge problem. Again, Chinese English is one story, but there's 6,000 languages out there waiting for some help. And the other question is, how do we go domain independent? In domain independent, we also distinguish between cooperative speech translation at telephones, two people wanting to understand each other, or uncooperative, when you want to get an interpretation or a translation of two foreigners talking to each other monolingually in another language you don't understand. So this would be our challenges here. Here you have two foreign speakers and the third one wants to understand it. And here you have a lecture that you want to have translated from one language into the other. This is a laundry list of research challenges. Human factors is very important, but I will not say much about it. This is, again, how do you deliver this information? Robustness, how do you do this under noise, etc. I talked about it in the chill story a little bit. Multilinguality, different languages have to have different properties, different morphology, different. Some are tonal, some are not, some have different scripts and so on. That's an extra challenge. And then the important one, I think, or the interesting one I want to spend a little time on now is the portability. So the portability agenda is this. If we can do something in one language pair that has a lot of data, that's good, but with 6,000 languages, we need to dramatically reduce the cost of doing this. The development cost is still way too high for most of these languages. It's also not clear whether they will come online fast enough with the amount of data resources that we have in English and Chinese. And so it's important to look at what we can do at the speech, machine translation, synthesis, dialogue level to accelerate the process and make that cheaper to do. And is it possible to do language independent or adaptive processing? Here's one result from this work. This is work by Tanja Schulz. She did this as a PhD work. She's now on the faculty at CMU working on this problem of how can you build speech recognizer with much less data and bring them up to speed in new languages much more quickly than before. So this is where she started. She would take basically a new language, Portuguese, and present it with acoustic models from another language. And you get an error rate of 70%. If you train a recognizer on Portuguese with the data she had, 16.5 hours of speech, you get an error rate of 19%. And her challenge was, can we do something with multilingual acoustic models from other languages to, in fact, get a reasonable result in a new language that we hadn't seen before? So what she's done is she basically took data from 12 other languages that have nothing to do with Portuguese, or certainly are different languages than Portuguese, and trained a big acoustic model on all of these languages with an acoustic phonetic tree, and given some data in the target language, Portuguese, allowed for some amount of adaptation to that new language, and then was able to show that with half an hour or an hour and a half, she gets actually quite respectable performance in that new language, almost equivalent to actually training it with a complete set of data. So it was a nice result to show what we mean by saying the portability can be improved if we somehow come up with new techniques for more rapid adaptation or more better transfer to new languages. And machine translation, that is also a difficult issue, is how can we rapidly adapt machine translation system to new languages. One thing we could do there is simply improve the modularity, make them more modular so that you can reuse, for example, grammar rules. Or we could try to do more, if you believe in the more statistical approach, we can use more effectively monolingual data, and that's in fact a winning strategy. Because parallel corpora are certainly harder to come by. And then we experimented with 4 different approaches, which I'll just give you in a nutshell the idea. One is unsupervised grammar inference. That is, again, work that Yi Wang did a while ago. And the notion is this. You take just, in a certain domain, lots of data, and you can, in an unsupervised way, by clustering algorithms, extract key phrases and key word classes from this without actually having to write grammar rules and so forth. So this is a picture from Ye's work a while back, 97, where you would find, for example, certain word classes simply by clustering mechanisms where you have 4, 5. This is in a scheduling scenario, 4, 5, 6, 7, 11, lunchtime. So all the things that are hours of the day. And here you have prepositions till, until, at, around, after. And by actually looking at word classes and then also sequences of words or sequences of word classes, you can actually iteratively build up trees that of frequently occurring word classes, but also frequently occurring sequences and frequently occurring sequences of classes and so forth. And you see how that actually builds up a tree. Helen Ming in Hong Kong actually taken that idea or a similar idea, in fact, then did a more semi-automatic way, where it was supervised, but she then would also go look at the result and simply throw out things that were spurious, noisy, things that don't fit, and then retrain and get quite reasonable grammars from this in an iterative way. Here's another idea that another graduate student, Marcel Gavalda, got his PhD with. The notion here is a completely different one. You say instead of doing unsupervised grammar inference, here you're doing a supervised grammar inference. But again, the first thing you could do is supervised grammar inference. Let's just build a big tagged corpus and then have some statistical or neural net or whatever technique to learn how you map from the sentences into the representation. That's, of course, good. Many people have done it. The trouble is you now have to produce the tagged corpus, and producing the tagged corpus is probably almost as painful as writing grammar rules, I would argue. Creating tree banks is not trivial. So we went here a different route by saying there is an ontology or a representation you'd like to have, and you're willing to build a very simple seed grammar, but now you're letting the system grow through the interaction with the user who doesn't even know that he or she is writing grammar rules. So parents do that with their children. They write grammar rules in the heads of kids, basically, without noticing. And so we wanted to do that too. He had on the internet a little dialogue, and then if people type in or say a sentence where they would say, I need a hotel room for tomorrow, the system knows that means making reservation. But if you say something like, tomorrow I need a place to crash, then the system doesn't know that you want a hotel room reservation, and it would then basically try to guess where this phrase might fit in your request and propose a meaning for that sentence, and then query the user if that's the intended meaning, and if so, make it part of the grammar rules. That actually worked nicely. He could show that from an initial kernel grammar on user sessions and kernel grammar on independent corpora, you have fairly bad results here. And after these user sessions, new grammars would emerge that worked, first of all, very well on the training set, but then also worked quite well or generalized well to the unseen test set. Here's another thing. Again, the idea with the interlingua can be also used in combination with the statistical machine translation approach. And so another thesis we did here was to say, well, let's try to treat the interlingua as another language and build a statistical translation system between the input sentences and the interlingua to do that mapping for us. You have to change the mathematics a little bit because interlingua are tree structured and the branches on the tree are order invariant, so the mathematics of the formulation change a little bit, but you can then do it and train such a system and in fact get results with it, and it has been done successfully in that thesis. There's of course one trouble is you now have to have a tagged corpus, which is just what I said before, one additional effort now that you have to do. But what we wanted to do is at least see whether we can minimize that tagging effort by doing it only once. So the idea here that we also explored was a notion of grammar projection, and again it's published in ICSOPO2, where we said, okay, well, if I do this once on English and interlingua, can I then use that tagging and apply it to French or German simply by having a human being translate those sentences into French and German? And that actually worked quite nicely. You can just simply project those mappings, if you like, that the statistical translator has done in one language onto the other languages and don't have to do the tagging over again. And then have an interlingua-based system in the end. So that's the story. We have modularized grammars. We have we can write grammars without telling the people interactively, but that still takes time and domain limited. Statistical and supervised and semi-supervised grammar training, but all of these things still take some time. So we are looking yet at another method here by saying we can build statistical domain unlimited spontaneous speech translation systems. And if we do that, we need to look at, if we want to go in this additional direction to be domain unlimited, we need to, three things happen. One is what does it mean to have an interlingua in a domain unlimited system? That's of course a big problem because defining an interlingua in that case is a can of worms. And so one thing we're exploring is to see, can we use maybe English as an interlingua, or perhaps a linguistically enriched English or a simplified English as interlingua, and I'll show you a result on that. And then what do we do when we build a machine translation system and combine it with speech? Problem with that always is if you try to do a domain unlimited text translation system and you have a conversational speech system, the transcripts you're getting out of a conversational systems really don't match very well in style with the text that the text translation system has been trained on. And so these are the two lines of work that we're currently pursuing here. So with English as an interlingua, we say, well, if we can somehow simplify or normalize English as an interlingua, A, it's readable, but B, we can actually apply lots of linguistic resources that are available in English to do that, and we have to do that only once. So that could be a win. So does it work? So we did some experiments with hotel reservation dialogues where we trained a Chinese to English system and an English to Spanish system, and then evaluate Chinese, English, Spanish, and then enrich this English with a whole bunch of linguistic tags in the hope that it helps the translation process. And again, if that works, it would be a win because you do this only once and you do it only on English where you have these resources. Again, if we wanted to build Pashto Catalan translator, having all these resources in Pashto or Catalan would be impossible, but in English it certainly is possible. So here we did it in Chinese English. This system, we also have this is a statistical translation. We have two versions of the statistical translation system, which are shown here as results, and we compared also with Systram. Chinese English works quite well with both these statistical translation systems. Oh, by the way, this is also the NIST score as an evaluation scoring technique that's used in the IELTS community now. Now, English to Spanish, Systram turns out very, very good. We don't have that much data here in the statistical systems, but you see also here a particular result. And now if you train Chinese to Spanish, result is much worse. And the reason is not because Chinese-Spanish is necessarily harder, but because we have less data. So in this case, we can actually apply a lot of systems that we already had the benefit of lots of parallel corpora and training data, while for Chinese-Spanish, we didn't find that much. So you have a drop in performance. Now if you go this Chinese-English systems and English to Spanish system here, you actually raise the performance again considerably. So in summary, because of the win you have in terms of training data, you're really gaining here in the cascaded direction. Now, if you enrich the English in the middle with this linguistic information that I mentioned, you get a further gain. So that seems to also be a promising direction for us.
What if you went from Chinese to English interlingua back to English again, how much would you lose in the 6.7?
If you went from Chinese to
English interlingua and then to English. Like how
we
much
never did that. That's interesting. But I don't think it would matter. I think most of the changes that were made here is in fact adding information. So you would just throw away the information. So there's an n-best list and lattices, morphological analysis, sense guesser from WordNet, synonym generation, part of speech tagger. So if your target was those very English sentences, you just throw away the tags and get the same result, I think. But that's, of course, an unsatisfying answer, yeah.
I have a question about the previous slide. What allows you to compare the numbers in the different rows? Because I noticed that the Chinese to English, the number is much larger than... Are lower numbers better?
No,
higher numbers are better, okay. Is this the exact same text, or the same semantics in all of these?
It's the same test set, but again, keep in mind that all of these systems were trained on different corpora and different amounts of data, and that's in some sense the point of the slide, is you cannot really say that Chinese to speech is harder than Chinese to English. So if you had a lot of Chinese-Spanish data, training it directly would be your preferred method, because you would get the numbers that are comparable to this. It's only, the point here is you typically in some exotic languages don't have that, and then this is your next best choice.
So what exactly are these numbers? Like how do you evaluate these systems?
These are NIST scores, and they were computed on a single reference of the test sets.
Similar to Blue, right?
Yeah.
So it's speech to speech.
I'm sorry, that's the transcript of the speech, so it's text to text.
It's text to text.
So it doesn't contain any speech recognition errors. And Blue you're all familiar with is so. Okay, so as part of what we're doing with Interact, the ultimate speech translation machine is something that does anything you want: telephone, lecture, meetings, TV broadcasts, and so on. And the problem that you have in doing this is that the syntax and the structure is violated, right? And that's what we did in the domain limited systems. The way we dealt with that is by saying, well, we know what you typically have as semantic frame, and we're trying to extract these nuggets from the input and mapping them onto that representation. But now the semantics is too large for us to model or to have a hope to cover all the semantics. Again, you might argue with me on that, but it's certainly more challenging trying to cover the entire semantics of unlimited domain. And then insufficient data parallel corpora for conversational speech. There are no parallel corpora that translate to call home or switchboard into reasonable translation. And then the question is, what does a reasonable translation mean in the first place? Do you want to have all this garbled junk that people produce actually translated word by word? No, you want to have it somehow reduced. So the approach that we're taking is we're taking a conversational speech recognition engine that we develop in our lab. We have Chinese and English and Arabic speech engines that we can apply here. And then we take a text machine translation system like the one we're developing for TIDES. Currently our best one is the statistical machine translation system. But then something in the middle is missing, and we call that cleaning, compacting, rewriting. So you want to have a garbled, spontaneous utterance, and then clean it, compact it, and rewrite it in such a way that it acts or appears much more like a textual sentence that is then more suitable for the text translation. And the trick here is to work with lattices, so we can deal with errors, and then apply adaptation at all levels. Here's one first result along those lines. Is basically we did just that. One student did a first shot experiment at what does it take to take this fluent ASR output and create something that is cleaner so that we can send it into natural language understanding or machine translation. And we did this also in the source channel approach, source channel model approach. And the beauty of that would be is now we have then a cascade of 3 systems that are all source channel models, where you have the recognizer, one thing, then the cleaner, summarizer, whatever, and at the other and the machine translation. So if you have three cascaded statistical systems with a very similar approach, there is a possibility for actually a lot of interesting joint tuning and optimization going on. So here's some examples of what happens. The travel agent might be able to help you out with that too. Output was the travel agent might be able to help you out with that too. That's fairly easy, I would say. So we want to try for an arrival Friday morning, I think. We want to try for an arrival Friday morning, I think. So it's actually doing some interesting things here and reducing or simplifying the text. There's, of course, errors, as you can see down there, where it doesn't do everything as well as you'd like to. So we've done something else as part of Interact. All these experiments were done for small tasks. So now we do attempt lecture translation, and that's actually currently going on, so I can't tell you the full story yet, but this is what we're currently doing. We defined as part of the Interact Center, we sponsored a workshop, which is much like Johns Hopkins workshops for 6 weeks, sort of a brainstorming activity. But it's carried out in 4 different sites. It's done in Karlsruhe, at CMU, at ISI in Los Angeles, and in Tokyo at Furui's lab. And all of us basically got together for a kickoff meeting and defined the tasks and the data and so forth, and now everyone disbanded into their respective labs and is doing their thing. And then in middle of October, we all go to Tokyo for the wrap-up session, where we all then report the results of this activity. And the goal of this workshop is to experiment with this cleaning summarization module. So we take the machine translation system and the speech recognizer as a given, and we say, what can we do in between to bring these things more closer together so that they match? Language pairs is English and Chinese for various data-related reasons. We actually did it, in this case, from English to Chinese rather than the other way around. And basically built these models. So I can tell you, again, the full results aren't there yet. There is actually 2 interesting results that have emerged that I don't even have a good slide for. One is that two surprising things happen, that if you do some careful manual cleaning, you get substantially better machine translation results than if you feed the junk that comes out of a manual transcription from the recognizer into the translation engine. No big surprise here. But it's comforting to know that this is true. The second is actually, to our surprise, that running the Chinese-English translation system in reverse from English to Chinese worked actually surprisingly well, and we don't lose that much performance under comparable conditions. And the third one is that the first implementation of a cleaning module seems to be working surprisingly well in terms of precision recall, so that we're actually very much encouraged that this cascade will in fact also work. And we'll have probably more results in a week or 2, so unfortunately I'm speaking here a few days too early. There is, I'm sorry, I'm not sure if I want to say too much about this. This is one additional aspect of this whole problem is many of your translation problems in unlimited domain now also come through named entities. Named entities tend to be things like words and places and things, and the recognizer often has them as OOVs. The translators sometimes don't have them in the vocabulary, translation vocabulary. And so what you're seeing here is in fact a result of what happens if you take newswire and broadcast news. Sorry, I don't. What was done here is take newswire and broadcast news and compute performance in the translation of that. Yeah, and this is a semi-last slide. And now you put an ASR system in front of it, and you get a further degradation in performance. Much of this happens because of, this is the translation of named entities. Obviously because the named entities were substituted by something else. Now if you do in the source language and in the translation text, take in the source language, feed it into a web search for similar documents, retrieve all kinds of words that may be new, and compare them with the phonetic hypotheses or with the phonetic string that you're getting out of the hypothesis you did generate, and hypothesize that that may be the named entities or these new words that you were looking for. Now you can take the text with all its mistakes and also feed it through the translator, and in the target language also take the translated text and do the same trick by doing a web search or a text search in the big corpus on the target side and look for new words that might be in related text. And now you can actually even correlate the phonetic string of that new word in the target text and correlate it with the phonetic string of that new word in the source text, because names tend to be the same in both input and output language. And by comparing them, strengthen that hypothesis of that new word of actually being the named entity. And that was done here, and you actually get a nice big gain of recovering some of those named entities. So this is another piece of work here. Okay. Most of this I've said. So let me just simply conclude in saying, well, these are our two hot buttons, these multimodal implicit services through perceptual user interfaces, and providing speech translation in an unrestricted way. So speech translation, we want to allow for any translation. So I should be giving my lectures in the future in some other languages, and you should get the translation right there. And we want to be able to port it more faster to new languages, so that we can actually bring this to other cultures and languages. Anyway, thanks very much.